I don't know. All right, welcome back to Physics with Miyoshi. And today we're going to talk about work and energy. I have a volunteer here who is not in my screen, but he's holding up a book, and we're going to talk about what he's doing here in a moment. The objectives for today are we can explain the concept of work and energy, use work and energy in some problems, and then hopefully solve some problems. Okay? So, let's find out what we've got here. Here are some of the big concepts. Work is energy, and energy's got to be conserved. We're going to talk a little bit about potential energy, and especially gravitational potential energy. There will be some more later on. One of the other ones we'll talk about is spring potential energy. Conservation and non-conservative forces. I should say, yeah, conservative and non-conservative forces. And then kinetic energy. Energy can't be lost, but it can be changed. We'll talk a little bit about power efficiency and energy in a non-constant force. Okay? So those are the main things. We're going to go a little fast here today, but those are the main things we're going to talk about. So, work is energy. So, we have our volunteer over here holding up this book. And while he may be exerting some energy, we'll talk about in a moment whether he's doing any work or not. So, first of all, units of work are joules. It's a Newton times a meter. So if I move something along if I have a block that's got some mass here, what is the weight of that block? If I know the mass is m, what's the weight?
Mass times gravity.
Okay, so the force is my mass times gravity, right? So if I want to move that guy, there's my force. And if I want to move this guy though, oops, let's get rid of that for now. But if I want to move this, if I pull this along, oh, the m stayed there. That's okay. If I move that, the force that it takes to move that guy times s is the displacement, and then the cosine theta is the angle between the force I'm moving it with and let's see, this would be my force. Theta is the angle of the between the displacement and the force. Okay, so if I have some displacement d here, or s, I guess is what we use. If I have some displacement s, and I've got some force F, and I've got some angle between there, in other words, it's not just along the same path, then as long as S, well, then my work will be the force times my displacement times the cosine theta. Okay? Now, if they're parallel, in other words, my displacement and my force are in the same direction, then it's just the force times the distance. Okay, does that make sense? All right. So, and why is it the cosine theta? Well, if we look at this triangle here, then we realize that this component of my force must be the parallel component, and that guy is just F cosine theta. Okay? The other way you can look at this is if you were doing it vectorially, we could say that the work is the force dot product the S. And that mathematically turns out to be the same thing. All right, so here's the question. Yes?
So if there's no angle that the force is being pushed at, so it's just kind of like, so theta is 0, it's just the mass times the displacement, right?
Not the mass, but the force times the displacement. Yeah, so the question was if there's no angle between there, in other words, my force is just the same direction as my displacement. There's no angle there, so theta is 0. Then yes, what's the cosine of 0?
1.
Cosine of 0 is 1. 0 degrees, 0 radians. So then it's just, then that means my work must be the force times the distance. Or the S in this case, I guess. Good. Okay? Now, so, that brings us back to this question. My volunteer here, who has been holding this up for however long, basically kept it in the same place, right? So, go ahead, you can have a seat. How much work did he do? Why?
Because unless it's moving.
He did 0 work because there was no displacement. So in this case, my work is force times displacement times cosine theta. So this guy ends up being 0, so the work has to be 0. Okay? Now, did he expend any energy doing that? Did you expend any energy doing that?
Yes.
Okay, where was, if he expended work, and I asserted earlier that work is energy, where'd that energy go, or where's the work done then? It's in his body. His heart pumps blood, and that does move, right? So that's where the work is done. So even though he didn't do any physical work on the book itself, the book didn't have any work done on it, nor did his hand have any work. The book didn't do any work on his hand, therefore that didn't have any work. Yes?
Then how do you account for gravity working on the book, but
It didn't do any work on the book because it didn't move.
okay.
There was no displacement, so there's no work. Okay? So even though gravity does exert a force on it, yes. Gravity exerts a force on this book, but there is no work done either by gravity or by the person holding it up. Okay? That's a tough concept to grasp in the beginning, but we have to distinguish between force and work. Okay? Alright, so next thing. So that comes back to energy. Energy really has to always be conserved. We're going to do a bunch of different problems here, and all the problems basically are going to come down to this thought that energy can either be destroyed nor created, and it must be conserved. Well, if we have a system like, anyway, okay. So the energy, different forms of energy that we're going to have are, the main ones are going to be potential energy and kinetic energy. And usually when we think about losing energy, it usually think about heat. And if we think about putting energy into a system, we think about that as the work. So here's kind of an equation that you might think about. Energy initial is always equal to energy final. Okay? Now we can say that, but almost always we're going to put energy lost. And we're also going to add energy with work sometimes. Okay? So this equation is the main thing you got to remember, but there are going to be times when we put energy in, and there's going to be times when we lose energy. Okay? And then almost always, we're going to make this a little bit more complicated now as well. We're almost always going to say potential energy, initial, and kinetic energy, initial, is equal to potential energy final plus kinetic energy final plus our energy lost. And then of course over here, any work put in. Okay? And we're going to get even more complicated than that later on when we actually put different kinds of potential energy in there. We'll have different kind. And kinetic energy is just energy of motion. That is just motion, but we'll have different kinds of motion as well. Okay? But if we look at all the types of energy we have, mostly they come down to potential energy and kinetic energy. Okay? All right. So what's kinetic energy? Kinetic energy is energy of motion, and I got to mention that a second ago. And potential energy is just some kind of pent-up energy, if you will. So here's my book again. Does this book have more? Well, just what, if we think about potential energy of gravity, gravitational potential energy, then I'm going to tell you that the book has more energy here than it does down here. Okay? So it's got more energy up here than it does down here, and that's just because of the gravitational potential energy. And we'll talk about that here in the next slide. Okay, does this make sense so far? Yes.
When you hold it up higher, are you saying it has more energy acting on it, or it itself has more energy?
Okay, that's a good question. The question was, does it have more energy acting on it? So that energy is not a force, okay? There's no more force acting on this than there was down here, because the force acting on it is what?
Gravity.
Gravity. And in this case, it's just the weight. Okay, so the energy is not dependent, is dependent on this mass and its position, where it is. So if it's here, it has more energy than it does down here. Okay? Well, because
Or distance.
it's, okay, yeah, and we'll talk about that here in the next slide. Okay? So for me, okay? Alright. So, oh, yeah, this is good. There are these things called conservative forces and non-conservative forces. Now, if we go back to this equation here, our non-conservative forces are almost always these losses. Okay? Those are our non-conservative forces. Our conservative forces, for the most part, the one we're going to concentrate on most is gravity. So we know that gravity always acts toward where? Gravity always acts toward the Earth, toward the center of the Earth. And the formula for the potential energy, so we'll look at it this way. Potential energy of gravity, due to gravity, is always equal to mass times the gravity times the height, or the change in height. Okay? So if I have something that's moves from here to here, its potential energy has changed by mg times h. Okay, so if I have this book, and I could tell you what its mass was, or if I could tell you what its mass was, or I could tell you its weight was, I multiply that weight times the height I change it, and that difference in height is my gravitational potential energy change. Okay? Most of the time when we talk about this equation too, we talk about change in energy, but we'll talk about that later. Okay? So, mgh is our potential energy. Or you can think about it, my change in potential energy is my mass times my gravity, acceleration due to gravity times my change in height. Okay, these two equations are essentially equivalent. And then when it talks about conservative forces, gravity is a conservative force. And so what that means is this. If I have an object like this book, it doesn't matter how I get that book from here to here, or from here to here. Whatever the path is that I take, the change in potential energy, whether I go this direction, or if I come here, or if I come down and then up, or up and then down, however, if I go from here to here, my potential energy change will still be the same. Okay? So, what that means, a conservative force is conservative if its path independent. Oops, it's a T. Path independent. So in other words, if I have a guy that's going to come here, and I know it's going to change potential energy, it doesn't matter whether I come this way, or straight up, or around and about. All these, as long as I start here and end here, will give me the same change in potential energy. Okay? That's conservative forces. A non-conservative force, that's not true. If I travel different paths, I will have different energies. I'll have different energies. Okay? So those are things like air resistance, friction, and those kind of things. And we'll talk about those as well. Okay? Conservative, non-conservative forces. Oh, goodness. All right. We talked about that just now. I did that backwards, but that's okay. Kinetic energy. Kinetic energy, I'll write this out again. Kinetic energy is energy of, what did I mention just a moment ago? Energy of motion. and the energy is 1/2 mv squared. Now I should say most of the time it's linear motion. We'll talk about angular motion later on. And the one, kind of going out of order, but the one rotational thing that we need to remember, or we need to find out, and I'll talk about this later, but there's going to be a couple problems we're going to do where we have to know that centripetal acceleration, which we'll talk about later. Just write this down for now. We'll explain it a little bit more. Is v squared over r. Okay? So kind of put this in your memory banks for a little bit, but we'll come back to that later. Okay, so kinetic energy. Energy of motion. Notice here that it has my mass. So as I take my same book again, and I drop it, okay? It started out with how much energy, how much kinetic energy to start out with when it's not in, okay, good. Because my speed was 0. Just before it hit the ground, it had its maximum, in this case, its maximum speed, and that is determined, that tells us how much kinetic energy there was. Okay? So as long as I know my speed and I know my mass, I just multiply it by, multiply the half times the mass times the speed squared. That gives me my kinetic energy. Notice that this is not a vector. It's just a scalar, so it's just the speed. So it doesn't matter whether it's going left, right, up, and down. It only matters what speed it is. Okay? Direction doesn't matter. And by the way, if we go back and actually, if we just look here and think about kinetic energy, so what I just said, from what I just said, is kinetic energy or any energy, is it a vector or a scalar? Okay, it's got to be a scalar. Since direction doesn't matter, we know that energy must be a scalar. Okay? All right. Matter of fact, let's do a little quick problem here. Since I dropped the book, okay, I dropped the book. Let's do a quick problem. If I said earlier that my initial energy must be my final energy, right? Okay? And I know that my energy in this case, we're just going to assume it's all conserved. Well, it is conserved. We're going to assume that there's no losses. So my potential energy plus my kinetic energy initial must be my potential energy final plus my kinetic energy final. Okay? A problem like this, a problem would be if I have a book that weighs 1 Newton and I drop it 1 meter, what is its final speed just before it hits the ground? Or if I'm above the ground 1 meter and I drop it, what's the speed just before it hits the ground, or just as it hits the ground? Okay? Anybody have an idea how to figure that out? Well, let's do it here. Okay? So, I know I have a book that's 1 Newton. So that's its force of weight. Okay? And I know that it's going to have a height of 1 meter. And I drop it, so what's going to be my final velocity? Okay? What's its initial velocity? Sitting here. What's that?
0.
0. So what's my initial kinetic energy? 0. Okay? If I consider the ground to be 0, which it's technically not, but if I consider the ground to be 0, what's my final potential energy? 0. Okay? So now my equation comes out to be my initial potential energy is got to be equal to my final kinetic energy. Does that make sense so far? That looks good? Okay, so what was my potential energy equation? Remember? I know I just told it to you a little bit ago, but what do you remember? Okay? It's m times g times h. And so that's got to be equal to, what's my kinetic energy? Right there. 1/2 mv squared. Okay? Actually, don't have. Let's instead of making it a force of 1 Newton, let's make it a mass of 1 kilogram. Okay? Doesn't matter actually. It actually doesn't matter. Why doesn't it matter? Anybody see? Doesn't matter because if I divide both sides by m, the m's go away. And so my V squared must be equal to 2 times GH. And we've seen that equation before, I believe. So my V must be equal to the square root of 2GH. And the square root of 2GH, 2 times 9.8 meter per second squared times 1 meter. Oops, ran out of room there. So this guy now says V is what? Square root of 2 times, let's write out again, 9.8 meter per second squared times 1 meter is, whatever that is, square root of 20 meters per second. Does that look right? Okay, so whatever that number is, square root of 20, it's meters squared per second squared, or square root of that, so that's going to be just meters per second. Okay? And that would be my final velocity if I dropped whatever size object, if there was no air resistance, if we ignore air resistance, whatever size object I drop from 1 meter high, its final velocity as it hits the ground should be whatever the square root of 20 is, meters per second. Okay? Alright, does that help out? Does that sound okay? So, our first problem with energy. How to figure out the final velocity if we know we dropped something. Just by knowing how much kinetic energy or potential energy it started with. Okay? Alright. Now this equation here, right here, it's the loss. It comes back to this one right here. So it says the loss, if I rearrange this equation, just E in as E out plus the losses, then I come up with that equation right here. Okay, so this just says my energy initial plus, oopsie, is energy final plus my losses. Okay, so I just rearranged the equation. Well, it kind of rearranges the equation. Velocity is negative, so that's why it's arrayed. It says it that way. It says because if I rearrange this equation, right, that ends up being E initial minus E final. If you assume that that's always going to be negative, then that's why that equation says it this way. Okay? It's rather odd. But anyway. Okay. But our losses are always whatever you put out, whatever you get out, minus what you get in, that's going to be your losses. Okay? Final minus initial. Actually, this is more right than that. I might have to change the slide. That should be the other way. Because we almost always will get, actually we'll always get more work, less work out than we put in. Yes?
Can you just go back to the slide?
Sure. Question?
Just go down a little bit. Just got answers, solutions.
Okay?
Either you or people.
All right. So,
Yeah, perfect. Yeah.
all right. So, obviously I wrote this down wrong, but this should be this way. Energy lost, well, whatever we're losing, is our whatever we started with minus what we got out. So, how many folks have ever, how many folks have driven a car? Okay, and how efficient are car engines? Not very, right? They're anywhere between 30 and maybe 70% efficient. Okay, so that means that whatever energy you put in, there's going to be a loss of 30 to 70% gone out somewhere else that we don't know about. So we're always going to have more energy input than we have energy output. Okay? All right. And I think that comes down to, well, a couple more things. let's just talk about power for 1 second. Power is just work or energy over time. So, if I have energy divided by time, or work divided by time, that's just our power. And power is just how fast you can do something. So if I can do something, if I can raise this book faster, that gives me more power than if I raise it slowly. That's less power. Okay, so power is just how much energy you use per time. Alright, we'll use that not very often, but for now anyway. We'll use it later on. Again, this is something you want to keep in your back pocket a little bit, and then we'll use it later. See if I have anything else very useful. Efficiency. This is kind of what I talked about back here. Efficiency is how well you do, how well a machine or whatever you're working with gets power out or energy out. So efficiency is work out over work in, or energy out over energy in. Okay? So if we put energy into a system, if I have some kind of machine and I put some form of energy in, I will always get some other form of energy out that's less than that energy in. Okay? Alright, so the energy out is always less than my energy in. Always, 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 at least in the real world. And where does that energy go? Well, remember we talked about that a little bit ago. It always goes to some kind of resistance, our losses of some sort. We have friction, we have air resistance, those kind of things will make, that's why we get our energy out. It's got to always be less than our energy in. Okay, because of losses. Alright? And again, efficiency, whether it's power or work, why would it be just power out as well? So efficiency is power out over power in. Why can I say that those are equivalent? Well, what's power? I just mentioned a minute ago. What's power? That's the same as our energy out per time. And if I divide that by my energy in per time, times go away, so this is still energy out over energy in. Okay, that's efficiency. All right, I think I have a couple more things. Those of you in calculus, this will actually hopefully make sense, but area under a curve. If I have a force, and I have a force versus displacement graph, then the area under the curve, that's my work. That's my energy. Okay? So a force displacement graph will give you energy. So that's a useful thing about calculus. If I have just a constant force, notice it's just the area under that curve also, but it's a rectangle. And this is our force times our distance. Okay? And this has to be, of course, the force that's parallel to our work, our displacement. Okay? If the force isn't parallel to our work, then we have to use that other equation with the cosine in there, right? We'll come back to that later. Alright? And I think the rest of it is a couple problems, and we'll talk about more problems as we go along. But I know we did a lot of stuff here. Talked about it very quickly, but basically we talked about pretty much all this stuff here. Work is energy. Energy's got to be conserved. There's a few equations we went through. Talked a little bit about conservative and non-conservative forces. Kinetic energy is energy of motion. Potential energy is energy of position. And then we talked a little bit about losses, a little bit about power, a little bit about efficiency, and just a little tiny bit about energy with a non-constant force. Yes?
Could you go back to that last page yet?
Sure. That one right there?
Yeah.
Okay, so we'll talk about more about all this stuff. But thanks for tuning in, and we'll see you next time on Physics with Miyoshi.